In section 1 of this chapter, we're going to be looking at estimating the distance traveled using rectangular approximation. Really, we're looking more at area in this, estimating the area under the curve, which we saw in our introduction as something that can give us the distance traveled. But looking at the area, if we're going to estimate this, our goal is going to be take, for one thing, slice this into narrow sections and kind of turn it into a rectangle, because we know a formula for the area under a rectangle. The problem with doing this is, well, if we look at something like this, maybe I'm estimating with this rectangle, I have a little bit of area outside of my curve, I have a little bit of area left over inside. They're not quite the same size there, and I could maybe balance out a little bit, but this is only an estimate of my area. It's not going to be exact, and we're going to look at a few different ways to do it. They're calling this the RAM method, or rectangular approximation method, and there's a couple of different ways of doing that. What we might be looking at then is if we have this thing split up into different parts, maybe we're using, going from 1 to 3, we're splitting these into fourths maybe, so that we have really small rectangles so we don't have a big margin of error. And then each one of those we could kind of draw as a rectangle instead, and then find the area of each one of those. And so using my formula where area is equal to base times height and adding all of those together, notice each one of these then would have a base of 0.25, so I could just keep repeating that in this case, or even maybe write it as 0.25 times and then take the sum of the different heights. So in the first interval it's like close to 0, then maybe 0.2 or 0.1, 0.3, 0.4, and so on. And as these grow up, we would add each one of these things together until we get to this last interval, which is going to be a much greater area. We can add all of those together to estimate what the area is under this curve. Now there's different ways of doing this. One, we could use the midpoint approximation, where we look at the point in the middle here. And so to do that, well, first of all, our interval then would be b minus a. That tells us how wide our rectangle is. Notice that's repeated in each one of these methods. So we're just looking at the width. In this one, I gave the same width to every rectangle. But in some cases, we might want to make some of them narrow and some of them wider, but we won't be doing that today. Then we take, if we're using the midpoint, then we have to be looking at this other point here in the middle, and we're really looking at the y value of this. Now to find that, I found the point in the middle of here. Okay, so my y value, I'm finding the midpoint, that would be b minus a over 2, which is where this part of the formula comes from. And then if we were taking multiple rectangles, we would add all of those rectangles together. With left rectangular approximation method, if we're looking for one of those, we will first of all take our interval. Here we're going from a to b, but we would look at the left side of that, which in this case is a, and we're going to use that a going up to the curve. That will be the y value that we're using for this. And so we're estimating this using one side, which makes our calculation a lot easier than doing the midpoint one. But notice with the midpoint one, I've kind of got my area inside outside balanced out a little bit. So this one might be a little more accurate in this particular problem, but in other cases it might not be, or it might just be easier to use this one, and so we might use this one. With the right rectangular approximation, when we draw our rectangles, we'll be looking at the right side, in this case b, and so finding the area of this, we'll be looking at the value here on the right side for my y, and that would give me f of b. Okay, in this problem I want to find the area under this curve. We're actually going to estimate it, and we're going to start using the left rectangular approximation method. We're going from 0 to 3. So starting here on the left, 0, on the right, 3. And what we'll do first, after we graph this, we'll look at where these intervals should be. So since there's 3 intervals, they would be at 1, 2, and 3. Now the next thing I'll do is, since I want these to be using a left approximation, then in each one of these I'm going to start over on the left and draw the rectangle. So if I look at this last interval, the left side would be here at 2, and my interval would be going across like this. In the second interval, it would start at 1, because that's on the left side. And the last one, it's actually starting at 0, so notice there would be no area in that first one. So the area that we're looking at would be inside of these rectangles here. Now we should notice that this is going to be a huge underestimate. There's a lot of area that's not getting counted here, but we're looking more at the method right now. So we'll use the 0 as the left side of the first one. The next one, going from 1, our height if we just plug it into x squared, would be 1. And then our next one we're using 2, which gives us a height of 4. And we wouldn't use the 3 because it's not the left side of any of our rectangles. Adding that area up, that's going to give us 0 plus 1 plus 4, or an area of 5. Again, this is a big underestimate because everything's on the inside. Now we can make this more accurate if we take more rectangles like we did in this one, and that's how we'll make them more accurate, is by taking more rectangles. In the next example, we're going to use right rectangular approximation, but this time we're going to use 6 subintervals. We're again going to go from 0 to 3, but this time when I draw my rectangles, we're going to start from the side, so I would actually need to come out over here and draw my rectangles coming back down. Now notice this time, since I'm using the right side, everything's actually an overestimate. And now to calculate each of these areas, I would have to find the values. Now this time I'm going at 0.5, I'm looking at 1, I'm looking at 1.5, I'm looking at 2 and 2.5, and also at 3, and using all of those areas. And so my height at these different places, the first one over here would be 0.25, which you could plug in. The next one would be, since it's at 1, that would be over at 1. And at 1.5 would be 2.25. At 2, that would give us a 4. At 2.5, we get 6.25. And then at 3, our last one, will be 3 squared is 9. So adding all of these together, working that out, again we're using 0.5 as our interval now because I have 6 intervals going from 0 to 3. And so dividing 6 over 3, each one of these intervals has a width of 1/2. And so adding those together, we get 11.375. Again, this is an overestimate because all my rectangles are going outside of this curve. Now be careful here. We just did one with left, and we said it's inside. We did one with right, and it's outside. But that doesn't mean that right will always be outside and left will always be inside. So notice if I'm going to do left-sided rectangles like in this curve right here, then on one side when I start here, these are actually on the inside. But when I get to the other side of this curve, the left-sided rectangles are actually outside the curve. So whether it's an overestimate or an underestimate is going to depend on our picture more than the method that we're using. In this example, we're looking at a situation where we have something moving and measurements are being taken of the velocity every 10 seconds. We could think about this as driving a car or other vehicle that has a speedometer, and we're looking at the speedometer every 10 seconds and measuring what it is. So at the 40-second mark, we were traveling 30 kilometers per hour. At the 90-second mark, 35 miles per hour. Now, this doesn't give us any information about what's happening between 0 and 10. I might be speeding up and slowing down a lot, but we're going to be able to use these measurements to estimate what our speed is, kind of assuming that there might be a smooth curve here. So starting at time 0, we have a 0, 0. At 10, we have 44. At 20, we have 15, and so on. So if we plot all of these going across, we'll get a graph that looks something like that. It seems a little bit disconnected, but again, if we think of this, maybe assuming that we kind of have a smooth curve here, maybe something that looks like this. Of course, this is only an assumption. I don't know. Maybe at this point it goes way down and then comes way up and then comes back down again. We don't know exactly what's happening, but we're going to be able to, again, estimate, kind of assuming this curve here. But rather than using that curve, since we don't know what's happening, we're going to think about rectangles. Now we're using right rectangular approximation, so I would be thinking about it as, at this point, this would be my rectangle. For the next interval, this is my right side here, so I would be using at the 20, and this side it would be this rectangle here. The next one is coming down again and be over here. Now using all those measurements, then I could find my area. First of all, each interval then is 10 seconds, so I could use that 10 seconds as my base for all of these. So when I think about base times height for my area here, I'm just going to multiply the 10 on the outside and then take each of my measurements on the inside, because it's always 10 times the height, 10 times the height, 10 times the height. So my first interval using the right side would be this value here, which was 44. The next one was 15. So we don't really need to look at the graph. We don't actually have to graph this if we understand what it's doing. We can just add all of these, knowing that the right side would exclude 0, and we're going to keep adding all of these values until we get to 35 as our last value. Plugging that into our calculator, those will add up to 384. And don't forget that we are multiplying, each one had a base of 10. And so 3,840. Now we think about our units here, we are talking about feet per second and seconds, so the area under this graph would be in feet. And so we have an estimate of the distance that we've traveled in feet. Now that was using the right side of these. We can do the same thing using the left side. Now looking back at our graph, I'm going to use red for this. That would mean that our first one is down here. Our second one is actually going to be the higher one here. Our next one would be going here. So all of our left sides are going to be changing, it's going to be switching the order. So what's going to be different for the left sides is that we are going to start at the 0. We're not going to use the final one because at the final one our left side will be actually here at 110. So we can add all of these together. Again, we have a 10 for our starting position, and then we're going to start with 0 plus 44 plus 15 and so on until we get to our final value, which again is 30. We do not use that 35 because that's a right side. Working this out, those will add up to 349 or 3490, and our units again will be in feet. So this then is just another example of how we can use area under a graph to find the distance traveled.